Hello, welcome to EEE 117. This is Dr. Tracy Toops. Here we're talking about a new topic, one for every week. Here we're going to do Bode plots. Now, in your textbook, Bode plot is actually in the end. It's an appendix part. This is Appendix E2, I believe. So that's where we're going to pull our information from. So it does break the chapter order a little bit. Okay. So here we talked about Laplace transforms. We talked about transfer function. We kind of finished talking about some poles and zeros and looking at the transfer function and seeing what happens when you plug things into S, right? Because remember, the whole point is a frequency sweep. Why is when you put 1,000 hertz and 2,000 hertz, 3,000, 4,000, 5,000 hertz? We're going to get some trends going on. Here, we're going to talk about how to accurately graph the output as the frequency changes. So you have a circuit. At low frequency, your gain might be really high. And as the frequency gets higher and higher, your gain might slope down, right? And then we could graph that accurately. So the end results is when you have a circuit, you have a graph attached to it that will tell you this is the behavior of the circuit without actually having to test it physically. Like that's the whole point of this is when you want to buy equipment, you want to see a graph of the output so you know that the equipment's going to behave like you want it to for your system. That's the ultimate result of so I'm looking at circuit analysis, right? We're just trying to figure out what things do. Okay. So so far we've circuit analysis, we typically look at one circuit and just find the input and output and call it a day. But in reality, it's going to be multiple circuits in series, right? You might have like your iPhone and it's going to go to a receiver A, then it might go to amplifier B, and then go to speaker C. So in realistic terms, a signal might go through multiple stages of amplifications or filtering to get the desired signal to end. Now, when you think about power in versus power out, when you have multiple systems in series, you have to multiply the gain of each one. You have to find the gain of A, the gain of B, gain of C, and you multiply each of them to get the total output versus input gain. Now, within each circuit, you can figure out the gain itself. This is the, in this particular case, the output for A is P1, this middle section. Okay. So for gain, the output over input is P1 over Pi, because that's what from A's reference, that's what the output is, P1, and the gain is Pi. For circuit B, the output is P2, and the input is P1, which is the output of the previous circuit A. That's the cascading part. So for gain B, the circuit is P2 over P1. And then for circuit C, the output is an actual real output we want, P out. And the input is P2, which is the output of B. So yeah, you gain a C P out over P2. Obviously, if you cancel the P2s, P1s, you're going to get P out over P in, which is what we want. So the big thing I want to take away from this is note that when things are in series, we have to multiply the gain together to get the output. Okay? And by doing that, we can have an amplification stage, maybe a second amplification stage to really get that voltage high, and maybe a filtering stage to get out some noises. That's kind of what we're trying to think of. Okay. Now, the issue will come in is what happens when these gains get a little complicated. It's kind of hard to multiply multiple integrals together and hard math, right? We don't like hard math. So what a lot of electrical engineers did about 100 years ago is they decided it was a math trick. They realized instead of multiplying things together, it's easier to add things, right? I mean, I think we can all agree adding numbers are easier than multiplying numbers. So mathematically, you could take the gain and take the log of the gain. And remember what logs do. Logarithmic functions would take multiplication, division, and turn it into addition and subtraction. Okay, so if I have a log of P out over P in, which is the gain of A, B, and C, you could split up each individual gain towards log 10 of gain 1A plus log 10 of gain B plus log 10 of gain C. And that's what a lot of electrical engineers did back then because it was easier to figure out the gain of each circuit and then add them together, not multiply. Okay. So this is a very common feature they did back in the early days of telegrams and telephones and Morse code and all that stuff. Like the, like Wild West era, basically. Now, the unit that comes out of this is called a decibel. We take this amplitude, we take this gain multiplied by 20, and just some people a long time ago said this is gonna be what a decibel is. Okay. And the decibel, which I'm sure you've heard of somewhere, is a measurement of how loud something is. It's a measurement of the gain of a circuit. Okay. So you could literally say you have a decibel level of the circuit gain, which is always equal to 20 log 10 base 10 of the gain of the circuit, the voltage gain, V out over V in. Okay, so just go ahead and burn this in your brain. The decibel gain of a circuit is always 20 log 10 of the voltage gain, V out over V in. Okay. And we're going to use this for a lot of our circuit analysis moving forward. Now, let's kind of talk about where does the gain fit in. You have a circuit here, it's an amplifier, let's say, a home audio system. You have an input signal, input voltage, input current. This is coming from, I don't know, VCR if you're like in 1980 or something, right? Or your PlayStation or your Nintendo Switch, right? So you have a signal coming into the amplifier. The amplifier will amplify the signal and it'll go out to your RL, which is your speaker, your home audio system. So there's a gain of the circuit as we amplify the sound to make it sound better in your living room. The gain of the circuit can be figured out as 20 log 10 of the output voltage to the speaker compared to the input voltage from your PlayStation 5. And that's in decibels, which is a shorthand called dB, right? So if you ever have a home audio system, you ever have a giant knob you turn, you can probably see the dB scale rise from like -60 to +60 or some value, whatever the range is. Okay, it's a measurement of how loud the system is or how much you're amplifying the input signal from your PlayStation 5, right? The way you can relate gain to hard ratios, because they're different. The dB and the regular ratio are vastly different because of the log 10. A dB of 0 means you have a gain of 1, meaning you're not touching the signal. So if you ever have an amplifier, you put it at 0 dB, it's whatever signal is going in is the same one coming out. We didn't make it bigger, we didn't make it smaller. Okay. If you raise the gain to 3, your ratio is going to be 1.41 or square root 2. Right? dB gain of 6 is 2, and so on and so on. The big ones we typically look at are the groups of 20s. If you have a dB of 20, that means your gain is 10 times what it originally was. If you have a gain of 40, that means you're at 100 times. If you have a gain of 60, it's 1,000, 80 is 10,000, and so on. Okay. So as you can see, dB scale rises exponentially because it's logarithmic to begin with. Remember, logs and exponential kind of go opposite directions. So as a linear increase in dB scale in the logs in the log domain, when you convert it back to the regular domain of ratios, it's every 20 scale you add a 0 to the end of the gain. So it could explode very quickly. So for example, if our circuit has a dB gain of 20, this whole circuit has a dB gain of 20. I know my ratio is 10 times. So whatever voltage I put in is going to be 10 times coming out. So if my V in is 5 volts, my output is going to be 50 volts, and that goes to the speaker. Okay. So that's what the dB gain, that's what dB stands for. It's how much you want to increase the power circuit or the output. Okay. So like I said, the deck every 20 is kind of the big numbers we keep track of because those line up evenly to increase of 10x every time. I like to say every time we go up 20, we add a 0 to the ratio, 100, 10, 100,000, so on. Now it goes the opposite way. If you remember how logs work, if you have a negative log, it reduces the value by 10. You divide by 10. So a negative 20 dB means our gain is 0.1. A negative 40 means 0.01 and so on. So every time you go up 20 dB, you add a 0. Every time you go down 20 dB, even to negative dBs, you remove a 0 from your gain. Okay. Now, we said a lot of math, but how does that relate to you in real life? This is a good scale to show you the level, like the sound dB we have. There's lots of rules and ordinances of how loud something can be before we bust your eardrums. So the softest noise a human can hear is 0 dB, right? Me talking to you is probably normal conversation level. This is a 60 dB level of noise, okay? Office noise is probably something you're gonna be used to. People chattering and slamming on keyboards and stuff like that. Oops, sorry. Is that 70 dB? You hear clap, 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 right? Vacuum cleaners, hair dryers, right? Loud city traffic, that's up to getting to 100 dB. And you can see now we're getting to a scale where it's uncomfortable, right? People say usually a threshold of 80 dB is where people start having long-term headaches. So if you ever try to sit there in city traffic and hear all the motors and honking and blah blah blah, after like an hour or so, you're gonna get a headache, right? Or think about if you're in the subway and motorcycle, you hear all the exhaust, right? Leaf blowers turning at 6 a.m. for an hour. That's gonna suck. Okay, you're gonna get a headache from this, and that's not just psychologically a headache. You physically get a headache because it's damaging to your ears, right? Anything past that, we're talking about rock concerts, sirens, jets, fireworks, gunshots. These are painful level noises, and a lot of times OSHA and a lot of safety regulations says that you can't have noise above 110 dB. It's gonna literally you're gonna lose your hearing, right? So this is kind of just a range 0 dB to like 140, 150 dB. That's the big threshold range. Okay, where as you get to 150 dB, you're probably gonna blow your eardrums, which obviously you don't do that. Okay, so I just show you a real life comparison of noise in the dB scale from noise to what you hear and see every day. Okay, now how does this system of gain relate to circuit analysis? So you remember from last chapter, we have this physical circuit with inductors, capacitors. It could be a gain, it could be amplifier, we don't filter, whatever, right? Whatever you do, there's going to be an overall gain of the circuit. This is that transfer function we were talking about last week. Okay, the gain of the circuit is going to, in this particular case, is a flat 30 gain times s plus 10 divided by s plus 100, right? Where these are poles and zeros. We talked briefly. Anything on the denominator is a pole that tries to drive the circuit down. Anything on the numerator is a gain, is a zero that tries to drive the circuit higher. Okay. Now, what we can do is we can take this original circuit, 30 times s plus 10, s plus 100, which is in root form. And what we want to do is we want to try to minimize everything in the bracket as much as possible, get it to the smallest number. So the easiest way to make this s plus 10 smaller is to swap a 10 out. So we're just going to take this s plus 10 and then take a 10 out of it. The easiest way to do that, the 10 you could turn into a 1, but the s you need to divide by 10 to put a 10 on top and then take it out. So you can see this s plus 10 goes in the 10 times bracket s divided by 10 plus 1. On the bottom, you can do the same thing. We want to minimize this root as much as possible. So we pull 100 out, so we get s over 100 plus 1. Okay. And what we can see now is after we take 30 times 10 divided by 100, right, crunch this number down, we have three major components to the gain of this circuit. We have a flat 3. That's a flat gain across all frequencies. Right, because remember the whole point of this is we're going to do a frequency sweep from 0 hertz to like 10,000 hertz. We're going to see if the graph goes up and down and what's the gain as it changes. Okay. We have a 0 on top, where the 0 is set at 10. Because remember, S, we can plug in JW to get hard frequencies, and the middle point at 0 is where W equals whatever is divided here, right? We want to try and make the circuit eventually J1 plus 1. Okay, remember last week, that's the point where we saw that the gain starts increasing, right? Whenever this W is equal to this, where the 0 is. Okay. Same thing for the pole. You see how we have a JW divided by 100. So if we plug in J100 over 100, we're going to get J1 plus 1. If you remember, this is the point where the circuit starts taking off. Something happens at this level. So we can say this pole is 100. So overall, we got three things. We got the gain of 3, a 0 at 10 at the top, and a pole of 100 at the bottom. Now, these are three gains, like we talked about before. This is gain A, this is gain B, and this is gain C. Okay, they're multiplied together. Now we want to split them up to where we can add them all together. So the easiest thing to do is take the 20 log of this whole circuit. Okay. Now remember, what we do is when we do log, division multiplication gets split apart. So your answer will be 20 log of 3. So that's one group. And there's always magnitudes here. Okay. Now, that's the first one. The 0 comes in because it's on the top. Above is a numerator. It's positive 20 log times what's in here. So plus 20 log base 10. Again, magnitudes JW over 10 plus 1. Okay, because imagine you can't fit imaginary numbers in the log. It's always going to be the magnitude. The third pole in the bottom, notice, is underneath the division sign. So if you remember from your somewhere in middle school math, when you take the log of a denominator, you subtract the answer. So everything on top of the numerator is added, everything on the bottom subtracted. So we're going to subtract 20 log 10 of JW over 100 plus 1, or the pole. So you notice the gain, the top stuff in the numerator will add to the gain and make it bigger, and the denominator will make it smaller because we're subtracting the gain. So there's always a kind of a balance where things are fighting. Poles will always try to make negative gain and bring it down. Zeros will try to add gain and make it positive and bring it up. So remember, gains, poles go up. I'm sorry, zeros go up, poles go down in terms of gain, and they're going to balance out at some point. Okay. So here, there's three major components we're going to look at. The initial starting gain of 20 log 10 times 3. And this is constant for all frequencies, right? Remember, doing frequency sweep between 0 and 10 kilohertz. Okay, this number is not going to change based on your frequency. The pole, on the other hand, will lower the gain as frequency increases past omega equal 100. That was that cutoff point where something happened in the circuit. So as we're doing a frequency analysis, from 0 to 10 to 20, 30, 40, 50, 60, 70, right? We're putting the data points and checking our circuit. Once we reach 100, this gain is going to start decreasing because the pole is going to become active and the gain will literally start going negative. Or the pole will try to pull the gain down. The 0, on the other hand, will increase the gain as the frequency goes past omega equals 10. Okay. So remember, this is when that circuit turns, this part of the circuit turns on, and then we're going to get a positive gain on the output. And then, so anytime you're pulling 0, I say to kind of fight each other, right? The 0 tries to make the gain increase, the pole makes it go down. A lot of times they cancel out. Okay, and we're going to see that this week. But the main thing to know is three major components: a constant, all the zeros on top and all the poles in the bottom, and you could split them up into addition and subtraction by taking the log 20 log 10 function. Okay. Now we're going to go to each one and very specifically analyze what to do, right? Because this is where everybody always gets lost in the math. So remember, gain has three components. We're going to start with just a regular part, the constant gain, before we talk anything else. This gain is going to be 20 log base 10 of a constant. And your constant is going to be all numbers outside of poles and zeros. So if you remember our initial circuit up here is at 30. The 30 gets pulled out. That's the first part. Okay. Then every 0 in the numerator, multiply that into 30. So all the numerators come out of the brackets and you smash them into the constant 30. So you have 30 times 10. Okay, so purple 30 is that constant in the function. The 10 is the 0 on top. And you want to divide by the denominator, 100 for the pole specifically. Okay, coming back over is exactly what we did. Notice we pulled everything out the brackets. We had 30, which is a constant, times 10, which is the pole part, divide by, sorry, 30 times 10, and 10 is a 0, divide by 100, which is a pole. Okay, so this is kind of just like a shortcut method, just to show you exactly what to do. So multiply all your poles and zeros. If you have multiple zeros, you gotta add them, multiply them all together. You got multiple poles, you gotta multiply them all together. You gotta literally crunch them all into one number. So this is a hard number, you just crunch it. 30 times 10 is 300, divided by 100 is 3. Okay. So we literally take our calculator, 20 log 10 of 3 is 9.54 dB. You can literally get the calculator and crunch it. Okay. What does it look like on the Bode plot, the gain itself? Notice this graph. Okay, a lot of times we're going to use this graph. It's called the Bode plot. On the left-hand side, you're going to have gain. And this is magnitude in dB. Okay, because we're talking about decibels. You're going to start -40, -20, 0, 20, 40. And this could be as big or small as you want. You can do -100 and +100. But the big thing to note is groups of 20, 0, 20, 40. And it's linear. On the bottom, this is frequency, omega. This is actually a logarithmic scale. So if you ever heard, I don't know if you ever seen a graph that's a log graph. Log graphs on the bottom means that every major point you multiply by 10, right? They go by, it's like magnitudes, right? Order of magnitude, I would say. So at the very point right here, 10 to -1, this is 0.1. Okay. The next major point right here, this is 10 to the 0, which is 1. So this is 0.1, 10 to 0 is 1. The next major point is 10 to the 1, which is 10. And next major point right here is 100. And then, I mean, sorry. Yeah, 100. And then 10 to the 3 is 1,000. So we're literally going 0.1, 1, 10, 100, 1,000, 10,000, 100,000. So every major new point in the graph, you're adding a 0 to it. Okay. Right. And that's called log scale. So you probably can see it a lot in electrical engineering. A lot of times frequency is log scale. And the reason why is you can kind of figure out, well, maybe I want to know what's going on at the low scale right here. So we have a lot of granularity between 0.1 and 1. Okay. But then I don't want to lose all my information at 1,000. So I could crunch all the data up and keep 1,000 over here. Okay. So the way I like to think about log scale is log scale lets you put a wide amount of information across a very long scale onto one graph. Because if we went from 0.1 to 1 and it took what, about an inch of paper, you know how many sheets of paper we need to get to 1,000? It would be like 700, 1,000 pages, right? That doesn't make any sense. So let's use a log graph so you can see what happens at the very, very low scale, but still keep information at a very, very high scale as well. Okay, that's the advantage of using a log graph. So we're going to see this a lot. Just want to explain. And this graph put together, if you ever Google it, you probably hear something called a semi-log graph. Semi-log means that only half of the graph is in logarithmic, which is technically true. Only the x-axis here is logarithmic. The y-axis is linear because it's going from 0 to 20, 40, right? That's a linear scale. Okay, so this is linear. This is, sorry, logarithmic versus linear. So it's a linear logarithmic scale or a semi-log scale is what they call it. Okay. Now, for this gain, there is no frequency plugged into this graph at all, or this function at all. It's just hard numbers. So in terms of frequency, it's just going to be a flat 9.45 across the board. Okay. So this red line, doesn't matter what the frequency is, this component will always be 9.54 dB, which is a raw gain of like 6. Okay. So that's a big advantage. That's a big thing to note is this is constant no matter what the frequency is. It's always going to multiply this circuit by a flat amount. Okay. So that's the first one, the straight gain of the circuit. Now, we're going to talk about a pole. Remember, the pole is what's on the bottom. That's that's in the denominator. Okay. So the way a pole works is you'll have negative 20 log 10 of, I just chose one today, JWP over 10 plus 1. Okay. Here, remember we talked about doing the frequency sweep. What happens when we have a very low frequency to a very high frequency? Let's sweep across it. Well, let's start at omega equals 1. So whenever omega is much less than the actual pole, so the pole number itself is 10 right here. Okay. So 1 is much less than 10. Let's plug a number in, J. So magnitude of J omega, which is 1, divided by 10. So you have J 0.1 plus 1. If you crunch out any number, it's going to be almost equal to 1. It's going to be like 1.01. Pretty much 1. And you take negative log 20, doesn't matter. Anytime you take a log base 10 of 1, it's always going to be 0. Okay. So when you have a very low frequency below your pole number, you're going to have a gain of 0 dB, which does nothing. Okay. Now, when our frequency reaches the pole, so omega equals 10, we're going to get J10 over 10 plus 1. That's going to be roughly equal to root 2. And if you're plugging negative 20 log base 10 to root 2, you can get a negative 3 dB. So you can see when we hit the pole level, our frequency touches the pole, we're going to start seeing a decrease in the gain. Notice we went from 0 to negative 3, so something's happening. Again, remember, this is where last time we talked about when we hit that pole level, we see the circuit start changing. And this is that change we're starting to see. It's a negative 3 dB. And anywhere afterwards, we're going to really start seeing a loss of the gain. Okay, so when we get to omega is much greater than the pole, so let's just say 100, which is 10 times more than 10 times more than 10. So J 100 over 10, that's J 10 plus 1, that's roughly equal to 10. Negative 20 log base 10 of 10 is negative 20 dB. Okay, so you can see we went from 0 to just about negative 3 where the circuit's starting to dip, and now we're really dipping pretty bad. Negative 20 is a lot. Okay. And every time our frequency goes, we add another 0 to 1,000, 10,000, and so on. You crunch this number, you can get another negative 20 dB gain as well. So if I have omega equal 1,000, I'm going to get a negative 40 dB. If I have omega equal 10,000, it'll be negative 60, and it's going to go lower and lower and lower. So we can see that it's going to be a flat slope. Every time we add a 0 to our frequency, which is a decade later, okay, a decade means adding a 0, you can get a negative 20 dB decrease. So the slope means every time a decade increases, we go more negative 20, more negative 20, more negative 20. Okay. So the big takeaway here is it's just proving the math that when we plug in frequency, we start at 0 and then we start chunking down negative 20 to negative 4, negative 6. It gets pretty bad. Okay. Now, we could graph that, right? That's the whole point of using this graph. So remember, every time we look at a pole, look at what's underneath the division sign right here. That's going to be your pole frequency. Before the pole frequency, it's 0 dB. At the pole frequency is when we're going to start decreasing. So you see this 10 to the 1. This is 10 right here. This is our point where we're going to start decreasing. So anything before, look at our dB. It's 0. It's flat. Nothing happens. But after 10, we're going to start cranking down. Look at the slope. The slope is negative 20 dB a decade. And every time we go from 10, we're going to go to the next decade, which is 100. We're going to put a point right here. It's going to be negative 20. So negative 20 at 100. And that slope going down is negative 20 dB per decade. And it's going to keep doing it forever. It's never going to stop. We're going to go to 1,000. Plug in 1,000 to this equation, you get negative 40. Right? And another, you don't have to plug in into you don't have to get your calculator and plug in every time. There's a pattern you see. Every time we go to another decade, every time we're adding a 0 to a frequency, we're going another negative 20 down. So you can see at 1,000, we're negative 40. And it's going to keep going down. You could imagine, I imagine you could guess what 10,000 is going to be. If 1,000 was negative 40, 10,000 is going to be negative 60. 100,000 frequency is going to be negative 80. It's going to keep going down forever. Okay. And what this tells me circuit wise is before frequency of 100, this pole does nothing to the circuit. It doesn't add, it doesn't subtract, it passes signal through. But once we go past 100, it's going to try to kill the signal. It's going to attenuate it. It's going to make it go to 0. And every decade later, it's going to try harder and harder and harder. Okay, you remember what is the gain of negative 20 dB? It's 0.1. What's the gain of negative 40 dB? It's 0.01. And you can see, I mean, it really kills the signal if you multiply by 0.1. Okay. So that is what poles do. They make the circuit attenuate and go down. The way I see it is you try to kill the signal. Okay. Now, anytime you're doing Bode plots, because you have imaginary numbers attached to it, you're going to have a phase shift as well. I'll be honest, the phase shift is not nearly as important as the magnitude, but sometimes you need to keep track of it. Okay. The phase shift for a pole is going to be a negative angle because it's on the bottom of the denominator. Right? You remember when you're using phasors, stuff on the bottom denominator gets subtracted out. Same thing here. Okay. So we could set some rules. Remember, I always say the analysis, let's look at the frequency as you sweep across the pole. Let's do a low frequency before the pole. So the pole is 10, right? We're going to have a very low frequency here, and we're going to have a J 0.1 plus 1. Okay. This is going to be roughly equal to 0 degrees. So we're going to look at our pole. You know, I'm going to draw it in, maybe to help out. At 10 right here, this is the definition of where our pole is, right here. Okay. We're going to look a decade before and ask what happens. So a decade before, it's 1. So if I plug in 1 to this equation, J of 1, we're going to have J 1 over 100, 1 over 10, which is J 0.1 plus 1. What is the phase shift of J 0.1 plus 1? You can do your calculator if you want, but J is such a small number, it's going to have almost no phase shift. It's going to be 0 degrees. So we're going to put a point right here. The decade before our pole, it's 0 degrees. Now, at the pole frequency of 10, we're going to plug in J 10 over 10 plus 1. So our inside this bracket is going to be J1 plus 1. And I ask, what's the angle of J1 plus 1? You do your calculator, but it's 45 degrees. And we have to subtract it, so it's negative 45 degrees. Because this is a pole, it's on the denominator. So at our pole point of omega equals 10, that's where this pole is located, we're at negative 45 degrees. And then we look at a decade after. So we looked at 1, we looked at 10, let's do 1 afterwards, let's do 100. So we're going to put 100, J 100 over 10, which is J positive 10, plus 1, right? Right here. What's the angle of this? Is positive 90 degrees. Now we got subtracted, and there's a subtraction sign in front right here, so it's negative 90 degrees. So we know at 100, a frequency of 100, we have negative 90 degrees. Okay. Now there's a big difference. In the magnitude, it keeps going forever, negative. But on phase shifts, imaginary numbers can only max out at negative 90 degrees, right? You can't, there's no negative, you can't, a J cannot go past 90 degrees. A negative J cannot go past negative 90 degrees, okay? So at 100 and onwards, it's going to be a flat negative 90 degrees. So the overall trend you'll see for a pole is find out where your pole point is. That's going to be negative 45 degrees. Go a decade before this to be 0, and it's always going to be 0 on that half, left-hand side. Okay. Go 1 decade after, it's going to be to negative 90, and it's going to be flat afterwards to negative 90. It always starts at 0, always ends at negative 90 for this individual pole. And in between those 2 points, you're going to have a slope of negative 45 degree per decade. So every time you add a 0, you're going to subtract 45 degrees. But again, you only go from 0 to negative 45 to negative 90. You don't go, There's no negative 135 for a single pole. That doesn't exist. Okay. So that's how you do a pole, the phase angle for a pole. So remember two things: phase angle for a pole, magnitude for a pole. Those are the two graphs we're going to look at. So every time we do this Bode plot analysis to find the gain of the circuit, there's always going to be two graphs you should look at: the magnitude and the phase angle. Okay. Now some people throw away the phase angle because it's not important, but assuming both are important, we have to look at both of them. Okay. Now let's do an example of this. Right? I spit a bunch of theory crap. Let's see some numbers. Let's see an example, work it through. So we have a very basic circuit. We have a voltage source with a resistor and an inductor. So it's an RL circuit. Seen this 1,000 times now. What's the gain of the circuit? Well, my V out is over the resistor. This is my output of my circuit. So the gain of the circuit is going to be R over SL plus R, where SL is impedance of an inductor. This is basic voltage division. Right? Now, we could clean this up where you divide by L on both sides. You have R over L divided by S plus R over L, right? Let's plug in some numbers. R is 10 ohms, L is 10 henries, just making the numbers easy. So our gain of the circuit, so H of JW, we're plugging in JW instead of S, is going to be 10 over 10 divided by S is now JW plus 10 over 10, R over L. So kind of crunch that together, it's 1 over JW plus 1. Very simple gain. Now, let's take the log of this. So you literally gain of the circuit, let's put in dB scale. So you can take the gain is equal to 20 log 10 of 1 over JW plus 1. Now, just looking at this, you could tell that there is a single pole at the bottom. See how JW plus 1 is in the bottom? That's a pole in the circuit. Okay. So we could graph this in particular. So just looking at this right here, let's kind of split the screen. What is the frequency of my pole? Where it's already in, this is the simplest you can get, JW plus 1. You can't get any more simple than this. The pole is when omega is equal to 1. So for this particular pole, I could say, actually I did one thing wrong. Let me change it. This should be negative. My apologies. There you go. Gain is equal to negative 20 log 10 of 1 over JW plus 1. So this is the pole. So here, notice that we're going to put a stamp, a dot right here at 1, because that's where the pole is located. Anything before the pole, the magnitude is 0. Anything after, it goes to a negative 20 dB for a decade. So I'm literally going to draw a line down here. Just make sure at the next decade over, so this is 1, this is 10 right here. 10 should be negative 20, and then 100 right here should be negative 40. It's going to keep decreasing. Okay, so this is literally the output of the circuit above here. Right here. So what this output tells me is when I turn on my function generator, if my frequency is 0.1, my gain is going to go straight through. A 0 dB is equal to a gain of 1, so you're just passing the signal through. Okay. Now, does that make sense? Well, let's look at this. If I have a very low frequency, what's my impedance of the inductor? It's going to be very, very small. Right? If omega is 0.1, so JW is 0.1, this is going to be impedance at 0.1, and R is impedance of 10. Or sorry, this impedance, if you take 0.1 times 10, is going to be on 1 ohm. And if R is 10 ohms, where's all the voltage going to go across? Right? You have 1 ohm here and 10 ohm here, all the voltage is going to go across the resistor because it's a bigger impedance. So at this point in case, your input voltage goes almost all to the resistor, none of it to the inductor. So you're passing the signal through. If this is 50 volts, this will be almost 50 volts. It'll be like 49 point something volts. So you're passing the whole signal through. Because you have a low frequency, the inductor doesn't do anything. Now, what happens when we look at high frequency? Let's go to 10, 100, 1,000. Okay, once we get to that point, what's the impedance of an inductor? Well, if omega is 100, we could plug in JWL, or J100 times 10, it's 1,000. So inductor impedance is 1,000, resistor is still 10. Who's the dominating impedance of these two? It's obviously the inductor. So where's all the voltage going to go? All the voltage is going to go to the inductor, almost none of it is going to go to the resistor. So at high frequency, the inductor kills the whole circuit, right? Which is by design. Okay, That's why you see the gain go to -40. What's the gain of -40? -40 gain is 0.01. You 99% of the signal just went poof. You killed it. Okay. So that's how the Bode plot is that's how the circuit ties into the Bode plot. It's just looking at the gain of the circuit based on how inductors and capacitors kind of do their voltage division in our case. Okay. What would the frequency, the phase shift? Well, remember how phase shift works. Figure out where your circuit, your pole is. Our pole is at 1, so draw that dot at -45 degrees. So pole is at 1, so think of this line right here, and then the middle point is always -45 degrees. Okay. The decade before we go to 0. The decade after we go to -90. So draw 2 more points and you draw a line. And this is a -45 degree per decade slope. Anything before 0 is always 0. So I kind of drew a dotted line, just represent it's always 0 before. Everything after is always -90. It's never going to change. So these are your 2 plots you would look for a pole at omega equals 1. Okay. So your Bode plot, magnitude, Bode plot, phase, in degrees. Okay. So this is where we're going to take our 15-20 minute break. I want you to do an exercise. We have a small RC circuit now. So you're going to have a R1 is 10 ohms, a C equals 0.1 farads, right? Calculate your gain, H of S, your transfer function, kind of like what we did with inductor. Obviously, it's going to be a little different because you got capacitor now, but I believe you guys can do that. Look at where your output voltage is across the capacitors this time. So do your voltage division and just keep track of your variables. Plug in R equals 10, C equals 0.1 to get actual gain of the circuit. Right? You should see a pole somewhere. And then calculate the gain in dB. Right? So do that in 20 log base 10 of that pole. Then I want you to graph it right here, just like I did before. Okay, don't forget you got a magnitude plot and you got your phase plot. Graph it here and we'll come back and we'll see how you did. Okay, so let's take that little small break and we'll come back in 15-20 minutes and see how you guys did. We'll see you in a little bit. Hello, welcome back to Triply 117 here. We're going to continue on Bode plots for the first lecture. We just talked about doing a exercise for these poles. So let's go ahead and check it out. So we have RC circuit where the output of the circuit is across capacitors this time. So we can look at a transfer function. This is going to be a voltage divider where V out is across the capacitor. So you're going to have the impedance of the capacitor divided by the impedance of the capacitor plus a resistor. It's the basic voltage division. Clean this up a little bit. You're going to have 1 over RC divided by S plus 1 over RC. So clearly there's a hole on the denominator. Okay. Go ahead and plug in JW, set H of S, and R and C as hard numbers. You're going to simplify all this to 1 over JW plus 1. So we have a pole at frequency W equals 1. So go ahead and calculate the gain in dB. So the gain of the circuit is equal to 20 log 10 of the magnitude of 1 over JW plus 1. Okay. Go ahead and graph this. Oh, by the way, this is the same pole in 0 as the example one, just to show you that even though it's a different circuit, you can still come up with the same answer. All right, so we have frequency of 1 is where our pole is. So we're going to go ahead and add 1. We're just going to slap this dot right here at magnitude 0. So this is a point where we're going to start sloping down the -20 dB per decade slope because this is a pole, and pole after you hit the frequency of the pole, it will start attenuating the signal and killing it. All right, anything before the magnitude is going to stay at 0 dB. Okay. Next, for the phase plot, we're going to look at omega equals 1 because that's where the pole is. That's going to be -45 degrees. You go a decade before, you can get a 0 degrees, and it's going to be flat before that. And in this case, that the decade before is 0.1. Go back to 1 where a pole is. We're going to go ahead a decade to 10. That should be -90 degrees, and it'll be flattened out the whole way through. So this slope is only good for 2 decades, from 0.1 to 1, and then 1 to 10, and then it's flat afterwards. Okay, so this is your magnitude response and phase response for a RC circuit where you output it across the capacitor. Okay. So let's go ahead and now talk about zeros because we talked about poles. This is the next logical flow. is, remember, 0 is the numerator on top of the function. So here we're gonna have a gain of positive 20 log base 10 of JW of 0 over, I'm just gonna choose 10 because that's an easy number, plus 1. So we have a 0 at 10. That's how we read this. So again, we can do a frequency sweep. We go from a lower frequency where JW is less than 0, as in the 0 point, right? We know the 0 point is 10, so we could say JW is equal to 1, J. So plug in omega W of 1, so we get J1 over 10 plus 1. Take magnitude, that's roughly equal to 1. And we know 20 log base 10 of 1 is equal to 0 dB. So again, what this shows us is before we get to the, as we do a frequency sweep, until we get to that actual frequency where 0 is, there's no change in the gain. It's flat 0 dB. Now, what happens when JW is equal to the 0, which is in our case 10? This is where we're going to have J10 over 10 plus 1, that's square root of 2. 20 log base 10 of square root of 2 is 3 dB, so we're going to have a positive 3 dB here. So right at this point, this is where we're going to start having a positive shift in the slope. We're going to start seeing a gain. Now, we haven't really, I mean, 3 dB isn't that much. So if we use something called straight line approximation, we could assume it's relatively 0 just to make the graph easy to draw. But it's good to know in real life, at this point, you will see a small gain of 3 dB. And then this is where the circle will start shooting up. So anything past this, we're going to start seeing some big gains. So let's see what happens when JW is greater than 0, 10. We're going to start seeing some gains. So again, what's a good point? Well, let's go from 10 to 100. So J100 over 10 plus 1, you get magnitude of that is equal to 10. 20 log base 10 to 10 is 20 dB. So you get a positive 20 dB. So it's a very big jump from this 3 dB to 20 dB. Okay. And so after that, you're going to get exponential gain. So every time we go add another 0 to a frequency and 10x it, we're going to get another 20 dB. So we go to 100 is 20, 1,000 is 40, 10,000 is 60, and so on and so on. Our slope overall will be plus 20 dB per decade. So it's very similar to a pole, except everything's positive, right? How do we graph that? Well, we can do it easily. So remember, before the 0 frequency is 0 dB. At the frequency, we start seeing an increase, and after the frequency, it's going to be positive 20 dB for the rest per decade for all eternity. So looking over here, if our 0 is at 10, so we put a dot at 10, anything before is 0, everything afterward goes up, a positive slope of 20 dB per decade. So we're going up, and it keeps on going forever. So notice at 100, we're positive 20, at 1,000, we're at 40. If I draw 10,000, we'll be at 60, and so on and so on. Okay. In terms of the phase shift here, notice it's a positive angle because it's a numerator, so it stays positive, right? We could go ahead and plug in the same omega equals 1, so you have J1 over 10 plus 1, phase shift is roughly 0. At the 0 frequency itself, here you have J10 over 10 plus 1, that's roughly a 45-degree shift. And then you do a at omega equals 100. So J100 over 10 plus 1, that's roughly equal to 90 degrees because the imaginary number is dominating so much. Positive 90 degrees. Okay. Again, just like the other pole, you start at 0. This time you go to positive 45 degrees and positive 90 degrees, and you stay at positive 90 degrees. You never go above positive 90 degrees for a single 0. Okay. So go ahead, graphically, what you could do, remember our 0 is at 10 for now. So we're going to put at 10, we're going to put a dot at positive 45 degrees for the individual 0. Go a decade below, before at 1, that's at 0 degrees. Go back to 10, a decade after at 100 is positive 90 degrees up here. And it's going to flatten out on positive 90 degrees. So the slope between 0.1 to 1 to, 0.1 to 1 to 10. From 1 to 10 to 100, the slope is positive 45 degrees per decade, right? And everything else is flat. Okay. So that's your phase shift. Again, the big difference from the poles and zeros is that for 0, the phase shift goes positive, the magnitude goes positive. A pole, it goes negative and negative. That's the only two differences. Okay. We can show an example of how to draw a 0 in a circuit. So we're going to have our mysterious circuit right here. We're going to assume this circuit has a 0. Now that's unrealistic, because and it has a 0, that means the gain goes to infinity, which will blow up the circuit. So in real life, you're not only gonna have a 0, you're always gonna be a combination of zeros and poles. But just to make the math simple and just to see it, we can go through it. So here we have h of s is v out of v in. This is 10 times s plus 1, s plus 0.1, right? So we take this s, we have a 0.1, we need to convert that to 1 to make the number simple. So how do you do that? Well, we multiply everything inside by 10. So we could pull we could pull a 0.1 out. Okay, so 0.1 gets pulled out. So we have a 1 in place of 0.1. To pull 0.1 out of s, we need to divide by 0.1, so we take it out. Okay. 10 times 0.1 is 1, so then our total gain of the circuit is 1, open parentheses, JW over 0.1 plus 1. All right, so what this tells me is we have a 0 at omega equals 0.1. Very, very low frequency, but it's there. Okay. The gain is now, notice, positive 20 log base 10 of j omega over 0.1 plus 1. Positive big deal because this is a 0. Okay, so we could graph it. The main thing we need to know is 0.1 is our starting point. So come over here. Notice in the graph 0.1 is right here, 10 to negative 1. Anything below is 0, and everything above shoots up at a positive 20 dB per decade. So we go to 0, then the positive 20, positive 40, positive 60, positive 80, and so on and so on. Okay. So main thing I want to do is I want to shift where the pole is. Previously we had a pole at 10. I want to put a 0.1 just to see how the graph changes. Right. Still the same shape, it's just shifted to the left to the right, depending on where your 0 is located. For the phase shift, here at 0.1, it's going to be 45 degrees. We go a decade before, it's kind of off the graph, I drew it anyway. This would be at 0.01. Right? Yeah, I can draw it real quick for you. Right? This will be at 0.0. Start up here. 0.01. Okay. That is at 0 degrees. And then we go to R0 at 0.1 of positive 45 degrees. Then we go a decade after to 1, and that's also positive 90 degrees now, and it flattens out at 90 degrees. So notice it starts at 0, a decade before. At R0 is 45, and the decade after is 90, and it flattens out. So the slope between these 3 points is positive 45 degrees per decade. Okay, now, big thing is, depending on where your 0 is, this is where the graph shows. If my 0 is at 100, all this will get shifted to this point right here at 100. Same thing here. This point will get shifted all the way here to 100 as well. Okay, so where your 0 is a very big deal on where this graph lands on where this slope lands on this graph. Okay, and that's the design part we can choose when we build a circuit. So in summary of all what you learned today, pole zeros and the standard dB. The whole idea of this is one, graph a transfer function by looking at 3 components. We need to look at the starting gain of the circuit. Right when we turn it on, that's your constant gain. We got to look at the number of zeros and their location, look at the number of poles and their locations, and graph those accordingly and take note of them. Okay. The total gain of an entire function, an entire circuit, will always be 20 log of all the constants in the top times all your zeros, and you can have multiple zeros, divide by all of your poles. Okay. Right? Put all these numbers, and that's going to be your starting gain. Remember, there's 3 things. There's that flat curve of the gain, that's 1, then all of your zeros and all of your poles. This is just to calculate that flat gain. So whatever, just these are hard numbers. There's no equations in here. And you number crunch this in the calculator, and you'll get like 9.5 dB. Okay. All poles in your graph can be graphed individually. It's 0 dB before you hit our pole location, and then negative 20 dB after the pole location. Okay. All zeros can be graphed that they're 0 dB before you hit their pole location, and there's positive 20 dB slope starting at zero location onwards. Okay, so that's all I have for today. Just wanted to cover 3 main points: that flat gain, the zeros, and the poles. Right, we're going to come back next week and we're going to combine it all together to show you how to make a combined Bode plot of the entire circuit. Right, today was just building blocks. Okay, so hope everybody has a good day, and we'll catch you next lecture this week. So you guys have a good day. See you around.